Hello, you. Yes, I know, it's my formal mode. After you've all had your dinners, I am... Stay. Okay. I am happy to introduce our guest speaker, Dr. Gordon Osinski. Allow me to read from the book of Osinski. Is an associate professor and the NRC MDA CSA CEMI Industrial Research Chair in Earth Science Exploration in the Departments of Earth Science and Physics and Astronomy at the University of Western Ontario. Main area of research focuses on understanding impact cratering, oh man, I forgot my glasses, as a planetary geological process, long arm sight here, folks.
Just stop now.
Oh, okay, fine. Thank you. Anyway, he's a really cool dude who does planetary geology type stuff. So Simon can throw things at him, I guess.
No, I was just going to second it.
Oh, you're just going to second it. Okay. Anyway, without any further utter silliness and stupidity, if I can introduce our speaker. Come on up.
Well, that's quite the introduction and quite the
Yes, I aim to please.
Yeah, so thank you. This is not the first slide. If you can we go back to, nope. You'll see the entire slideshow in reverse by the looks of it.
Can you give the presentation backwards?
I haven't practiced that.
So you're deconstructing.
Yep, absolutely. Anyway, it's a pleasure to be here tonight. There's a couple of familiar faces in the room. I think I gave a Rasc Ottawa talk maybe a decade ago when I was, I was based in Montreal at the Canadian Space Agency at that time, and since 2007 I've been at Western. And I do know there's a couple of experts in the room, so I'm going to assume that you know what a meteorite impact crater is, because there's a couple of folks to my right and left who I hear you hear from quite a lot in meetings talking about impact craters.
Once or twice before.
Yeah. Okay. So I'll skip the usual introduction I give, and I'm gonna hopefully look at both. This is a little interesting setup here because the screens are both sides. Going to talk to you about the role of impact events in the evolution of life and potentially the origin of life too. So I think hopefully it's something that's a little new. We're probably, when I say impact craters to a general audience, I know this is a very educated audience, it's usually things like the extinction of the dinosaurs and the destructive effect of impact events. So I'll touch on that today, but I really want to talk about what I've been terming in my research, kind of the beneficial effects of meteorite impacts. And so again, really preaching to the converted here. One of the kind of, there's lots of schematics of our solar system out there. I really like this one because it emphasizes, of course, produced by NASA, a couple of things. The two big things is, well, one big thing, space is not empty. We have the, let's see if there's a laser, oh, it won't show up on that screen. But we all know we've got an asteroid belt between kind of interior to Jupiter and Mars. And there's a good kind of diagram of a schematic comet coming in from the outer solar system. So I've seen some awesome photographs, by the way, from members of the Club of the Moon, and most of them seem to be of impact craters. As we know, even without the aid of a telescope on a clear night, you can just look up at the moon, and the moon is literally pockmarked by thousands upon thousands of impact craters. So the Earth should look like that too. Why don't we look like the moon? So I'm actually not an astronomer. I'm a geologist by background. And of course, the major reason the Earth doesn't look like the moon is because our planet is geologically active. Essentially, in a nutshell, the moon was formed. It had a bit of volcanism in its first billion years of its 4.5 billion year history. And then it really became relatively dormant geologically. And so since then, things have hit the moon and the record remains. Earth, because we're bigger, so because we have a bigger gravitational cross-section, we should be impacted by more asteroids and comets than the moon does. But we don't look like the moon, and of course, thankfully for us, we have an active planet. So we have plate tectonics, we have volcanism, erosion, we have a water cycle that continually recycles the surface of the Earth and destroys most of the record of impact craters. A lot of my research also focuses on Mars, of course the red planet, that is kind of little bit like the moon, but a little bit like the Earth too, and is a fascinating planet to study that I will touch on later on in the talk. So again, I hope fairly small screens, but hopefully you can kind of see from the back. So we now know of about 188 impact craters on Earth. Again, that number should be several tens of thousands if Earth was really like the moon. But again, of course, two-thirds of our planet is the ocean and the oceanic crust, which the oldest part of the crust under the ocean is only about 200 million years old. 240 million years is its maximum. And we know that the Earth is 4.5 billion years old. And so again, that part of the Earth is continually recycled. And I'm sure you've had talks from esteemed members of the audience that will point out that in Canada, we do have a tremendous record of meteorite impact craters. And if you can kind of zoom in, there are 30 impacts in Canada. The image is on the right-hand side there. And again, apologies, I guess laser pointers don't work on LED TVs. But on the right, kind of a pop quiz of kind of 3 fairly famous Canadian impact craters. We have a crater in the top right that is now known as Pingrelly, but it was New Quebec, and before that, I forget its name. Chubb. Thank you. In the middle is the Haughton crater in the Canadian high Arctic that I'll talk about much more, and of course Manicouagan down at the bottom right that I'm sure many of you are familiar with. And again, it's always nice talking about impact craters to this kind of audience, because I'm sure you've heard a lot of the history. I mean, it was Carlisle Beals, who was the Dominion astronomer of Canada, who really got the science of looking at impact craters going not just in Canada but internationally. This was kind of a decade before Apollo, where it really took off around the world. But he really pushed the search and then the study of impact craters in Canada. And I think you've had the likes of Mike Dents and Richard Grieve, folks from NRCan and the Geological Survey come here too. So we have a long heritage and a long history, and it's partly driven by we have some really awesome, well-preserved impact craters here in Canada. So the destructive power of impact events. I think the movie Armageddon came up on this table over dinner, and I forget how we got onto Armageddon, but I think it was in between the Newfie jokes and something else, from what I remember. The same year, of course, we had, and when I teach students about this now, it's quite bad, because I mean that was 1998, which. When the age of our students now are approaching that at first year undergrad. But we had kind of deep impact in Armageddon the same year. Don't know whether they timed it poorly or well. But this kind of idea, and it did, if anything, help kind of bring it into the public mindset a little bit, that large things do hit the Earth. I mean, it is incredible, alongside many things, even like plate tectonics, that 50 years ago, we didn't think, or most of the community in the world didn't really think that things hit the Earth. Even after we'd kind of looked at the moon and kind of figured out that those are impact craters on the moon and not volcanic landforms, there was still a lot of resistance to this idea that asteroids and comets can strike the Earth and affect the evolution of the geological evolution, but also kind of the biological evolution, which is what I'll talk about more today. So you definitely won't be able to read this plot. I usually try and show something like this because it really does put into numbers the destructive power of impact events. So on the y-axis is how frequently impacts of a given size occur, and on the x-axis is their size, is their energy in megatons, so tons of TNT equivalent. And you don't really need to read this, but I mean, I think a few of you may have been to Meteor Crater in Arizona. It's kind of the prototypical impact crater. It's about 1 kilometer and a bit across. It's already a couple of orders of magnitude more powerful and destructive, therefore, than the kind of hydrogen bombs dropped on Japan at the end of the Cold War, and still an order of magnitude more powerful than a typical Cold War era nuclear weapon, putting things into perspective. And of course, you keep going to the end of the scale, which is the Chicxulub crater in Mexico, that I'll talk about very briefly, that we think is associated with the mass extinction of the dinosaurs and lots of other life forms on Earth. And it's about 200 kilometers across as the size of that impact crater. When you look out in the solar system and you look at a telescope at the moon, that's pretty small. There are lots of crater a couple of 100 kilometers across. And of course, on the moon in particular, we have the South Pole Aitken Basin that we can't really see from the Earth because it's tucked around the limb that we don't get to see, but it's a couple of 1,000 kilometers across. And we know that impacts of that size must have affected the Earth in the first kind of 500 million years of our formation. And I'll come back to that later on. And so, again, very briefly, we now know this is the KPG mass extinction. Doesn't have the same ring as the KT mass extinction that it used to be called. The plot there, you don't really need to know what it is, but it's essentially kind of life's biodiversity going from about 600 million years on the right to the present day. And you would maybe expect that with evolution, we keep producing more species and life keeps diversifying, but it's punctuated. And again, those little black dots, it stepped. The last big step, of course, there's one that I'll just point out. There's always speculation about still. This is the Permian-Triassic boundary, 200-something million years ago, where something like 90% of all species on Earth disappeared. And you have to think about this for a second too. I mean, to get rid of a species, it takes a lot of doing globally. An impact event, if Canada was completely wiped off the face of the planet, humans would be around still. So to take an entire species off the face of the planet takes something quite extraordinary. Impact events have been proposed for that boundary, but it looks more like a huge volcanic eruptions in what is now Siberia is probably the responsible for that one. But the last one with the red circle is kind of the most famous, because that's when not just the dinosaurs, but ammonites and lots of other kind of cool, famous fossils that you'll see in German mineral shows and rock shops disappeared. And of course, kind of as I put down the bottom left that you probably can't read, it was actually hugely significant for us. It's one of those discussions you can have after another glass of wine or a scotch or something else, that if it wasn't for that impact event, dinosaurs may still be kind of dominating the planet. After that, mammals became the dominant life form on land. And so you can have an interesting philosophical conversation that we wouldn't be here today if it actually wasn't for that large impact event that wiped out the dinosaurs. And so we can leave that one for later. It was this is a great kind of a detective story too that again I could spend hours talking about. This event was proposed to be associated with the impact of an asteroid well before we had a crater. There's this famous iridium anomaly you may have heard about, and a paper that must be cited a gazillion times in science, where they found this peak of iridium, which is an element not really common on the surface of the Earth. And then it took another decade until they found it buried off what is now the Yucatan Peninsula in Mexico. And so I'll jog this. If you've got good eyes and you sat at the front, there is a very faint, it's about a 10-meter topographic change. And if you've ever been to Mexico, I haven't, but if you've seen pictures, you'll see cenotes, which are basically sinkholes filled with water. And that's what is around that kind of ring around the dashed red line. But it's buried beneath about 1 kilometer of rocks that have formed since. And again, I'm not going to leave this up tons of research since, so 1980 the first paper came out, and then about 1992 this crater was discovered, and then a lot of research in this community has looked at kind of the devastating and the destructive effects of impact events. And it is a long litany. You can imagine anything bad that could ever happen to the Earth. This one single impact event probably did it. Of course, locally, it's kind of game over for everyone and anything. Fireball, thousands of degrees Celsius. Hurricanes, tsunamis, earthquakes, we're talking kind of tidal waves hundreds of meters high, coming into the mid-US and a lot of central, what is now Central America. Near global wildfires for material coming out of the atmosphere, coming back in and igniting vegetation. Acid rain, because the rocks that this impact hit had a lot of sulfur in it. That goes up and falls out as rain. Something little known is destroying the ozone. Anything passing through the Earth's atmosphere will actually destroy a little bit of ozone. But there's proposals that after this impact event, the entire ozone layer was destroyed. And we know how critical that is for life. Global warming, and then, but just to touch on it very briefly, the kind of far right-hand image is an artist's reconstruction of a kind of nuclear winter in the aftermath of this. And we think that this is now the single biggest reason we had the mass extinction event was global cooling after the event of something like 10 or 15 degrees fairly instantaneously. And so, again, something just pause and think for a second. Climate change these days, we're very concerned, and we should be about a 1 or 2 degree average global warming over the next 100 years. This was something like 10 or 15 degrees almost instantly overnight. Humans were fairly adaptable. We can put on a jacket and we could maybe adapt to something like that, but most other species on Earth cannot adapt that quickly to something like that. So this is why I think asteroids and impact events got a lot of bad press. Not kind of surprising, I guess. But this is a question I want to pose now and kind of spend the rest of the talk on, which is the picture on the top right is, we know this first few 100 million years of history, we call it the Hadean, after a certain Greek god of the underworld and of hell. There's this idea of that's kind of what the surface of the Earth looked like. Volcanoes and things constantly hitting the Earth. But the interesting thing is that the oldest evidence of life on Earth now is about 3.8 billion years. I personally think it's probably going to go back a little further than that. And so the question is why, and more like how, did life originate on an Earth that looked like that? And so what I hopefully want to convince you kind of in the rest of the talk is how impact events after they form are actually beneficial for life. So I should have said at the beginning, I'm happy to make this interactive. So maybe if there are any kind of questions so far, I'm happy to answer a quick couple of questions, and or we can kind of keep going. If anyone's got a burning question. Yes?
Well, how long does it take for for things to settle out when we've got an image like that? You've got a situation where everything's basically on fire. How long does it take for the Earth to kind of settle out those temperatures and those conditions?
It's a great question, and to be honest, we don't really know. And I think that's partly because, again, you're reliant on geologists and reliant on the rock record. And I mean, if we go and look at the rocks and look at fossil recovery after that boundary, I mean, tens of thousands of years will be in layers of rock this thin. So it's hard to say whether things adapted and kind of went back to normal within a few tens of thousands of years or a few million years. So the errors are quite high. Interestingly, I haven't read the paper, but it's in my kind of list of papers. Just this week or last week, there was a paper proposing more rapid recovery in South America than had previously been thought. But rapid to them, I think, was still on the order of tens of millions of years. So again, as a geologist, that's fairly rapid. But yeah, the rest of us, it's not so rapid. But yeah, there's obviously some things, and I've tried to capture that on this plot. Some things are going to be, the effects will be quite quick, kind of the fireball and hurricanes and tsunamis and things. But it is things like the cooling. We really have no good handle on how long that. We think it happened fairly rapidly, but was it centuries or millennia? I don't think we have a good handle on yet. Yeah. Okay, so kind of enough of the doom and gloom. We'll move on to what I've kind of been focusing on the last few years, actually, which is the beneficial, telling someone earlier, I do a lot of work on Sudbury right now. Sudbury, of course, is a large impact crater, known for its also being North America's biggest mining camp. So I'm not going to talk about that benefit tonight, which is purely economic, but that is another interesting spin-off of impact craters. It's not just Sudbury, there are other impact craters around the world, several in Canada, Carswell in Saskatchewan, that's active uranium, was Canada's biggest uranium mine. And there's there's 3 or 4 craters in Saskatchewan and Alberta that produce oil and gas. And so actually from an economic perspective, we could have a whole other talk about the benefits. But I want to focus on kind of the implications for life. And this is something I wrote actually in the last year of my PhD, an article for New Scientist, and I always put this up. I didn't see the front page or the title until everyone else in the world did. The title of the article in the magazine is not this, but it's kind of interesting, and it's I guess a bit more contentious is how killer asteroids created Eden. That's kind of a theme that I want to talk about fairly briefly. You won't be able to read this, but this is quite timely, as just yesterday there's a paper in Science came out on. So earlier this year, the Chicxulub crater in Mexico, there was a long drill core sunk, and the first paper on that crater came out yesterday in the journal Science, and I'm a kind of low down on the author list. The paper didn't really focus on it, but if you can read the headline, and I'll try to squint, it's how asteroid impacts could create niches for life. And again, this is something that people have picked up on. This was an article in Physics Today, just kind of yesterday. And why is that? Well, the kind of idea is that impact events after they form can create habitats, so essentially habitable environments for, and in this case we're really talking about microbial life. Cyanobacteria, microorganisms, which of course when we're looking for life elsewhere in the solar system and thinking about life arising on Earth, that's what we're talking about. I have like a 2-hour-long presentation on this, but I was told to keep this to like half an hour at the most. So I'm just going to touch on one of these things today, which is hydrothermal systems. And I'm going to take you up also to the Canadian Arctic, which is where I've spent many summers now. So I'm just going to zoom back. Oh. So hydrothermal, in a nutshell, comes from 2 Greek words for water and heat. And so think of Yellowstone National Park, Iceland, New Zealand, where you have hot springs and geysers and steam vents. Basically, all you need to create a hydrothermal system is a heat source and then water. Put the 2 together, the heat source heats the water up. Hot water is good at dissolving rocks and other minerals, and it will do that. Hot water rises, it will cool down, precipitate out those new hydrothermal minerals, and then sinks again, and you get convection systems. On Earth today, all the active hydrothermal systems are associated with volcanically active regions, and so that's your heat source. But we now, and it's really only the last decade, think that just about all impact events, and again, I don't think it's that counterintuitive, can also produce hydrothermal activity. And so at Haughton, again, we're way up on Devon Island in the Canadian high Arctic. roughly on a parallel to Resolute Bay, which is where we fly out from. It's about a 45-minute twin otter flight from Resolute Bay. It's relatively accessible by Arctic standards. It's an absolutely amazing place to work. This is what actually brought me to Canada in 1999 to do my PhD, and it's kind of memories that never leave me is landing in New Brunswick. I've never been to Canada before, kind of never seen so many trees in my life, and then get taken up a week later up to Devon Island, which is a true polar desert environment. And so this is a satellite image, and there's no vegetation around. There's a tiny little speck of green in kind of the top left of that gray patch. That's about the only vegetation in this part of Devon Island, but it's great for doing geology because all the rocks are laid bare. So this crater, and hopefully you can see kind of some of the concentric circular patterns, it's about 23 kilometers across. So to me, and by solar system standards, that's fairly small, but I mean, you put 23 kilometer diameter circle over Ottawa, and it engulfs most of it, and then think of the ejector and all of the other deposits that would go around, and it's fairly sizable. The grey rocks are important. That isn't snow in the bullseye. If you go to the right-hand side, you'll see some white, and that's ice-covered lakes that are there at the height of summer. The grey rocks is rocks that are molten during an impact event. And so again, I didn't put in some slides earlier on that I often would do talking about craters, but asteroid or comet comes in, it's all about kinetic energy. And because it's half mass velocity squared, the energy released by impact events is huge, as we saw from that plot earlier on. And a lot of that is deposited as, or ends up as heat in the target. And so you can melt and vaporize rocks kind of instantaneously. And so again, the energy to vaporize a rock is quite considerable. So a lot of that material, though, ends up being essentially, think of like a big pool of magma, just lava bubbling around in the center of that crater after it formed. And so that's our heat source. On Earth, really and on Mars is another good example. Even if you have ice in the subsurface, that heat will melt the ice, you have rainwater, and you can generate one of these hydrothermal systems. And so again, a couple of kind of scenic photographs just to kind of show the type of terrain that you see on the way in the Twin Otter. And then kind of this is home sweet home, or was for many months earlier in my career, but I was up there again this last summer for a couple of weeks and still have students working on this site. So it's really quite an amazing environment. And this is July, and I like showing students this and things because it is a challenge. I mean, this was actually Canada Day one year, so July 1st, and a little bit of fresh snowfall. It introduces some challenges that you don't have in all parts of the world. And I think, and of course, another thing, especially again, think of me coming from the UK, where guns are very uncommon. I mean, people don't have guns, don't own them, and I got given a shotgun to carry kind of for field work and things. And so, thankfully, it's quite a I've got a bit less grey hair in that photograph too, I think. But yeah, different kind of area to work, challenging environment, but also kind of a very special place to work up in the Arctic as well. And so this was, I thought I had this slide earlier. This is kind of what if you could go to the Haughton crater after it formed about 30 million years ago, is what we would propose you would see around the rim of the crater, and I'll show you why, the evidence for that in a second. This is a picture of a typical spring at Yellowstone. And again, why we're interested is this very innocuous, inauspicious looking, I mean, what many people call like pond scum. It's primitive life, the gray, the oranges and the greens in there, cyanobacterial mats that are thriving in temperatures of well over 100 degrees Celsius. And so, I mean, these are quite fascinating, amazing organisms. The record now is a bacteria that is not just surviving, but growing, reproducing at 124 degrees C. I mean, but above the boiling point of water. I mean, it's just amazing. And so we have these extremophiles in many environments. They can grow at pH 1 or 2. 124 Celsius, almost huge salinities, huge alkalinities, kilometers down beneath the surface of the Earth. And so this is why this gets into kind of the space science and exploration type of the work I do. Is when I'm ever asked, do you think there's life on Mars? I'm like, I think there would have been, whether there is at the present day. But if life can figure out how to live in an environment like this, life is pretty adaptable. If it got going, I'm sure it's out there somewhere. It might be 10 kilometers down beneath the surface of Mars, if it ever took hold. So very quickly, I'll just show you some, this is a simplified geological map that we like to produce. And again, these images are going to be pretty small, but somewhere in there is a tiny rock hammer. It's actually about this big. So what you're looking at there is a cavity, quite a big one, kind of a couple of meters across. And we call this a vug. So you can see some greens and some oranges in there. This is iron sulfide, so kind of fool's gold, pyrite. These are minerals that grew from these hot fluids as they were coming through the crater. So of course, today this hydrothermal system is not active, but it left behind the evidence that geologists can find and kind of piece together. And so this is a great example. Impacts, of course, the other ingredient you need for a hydrothermal system is you have to get the fluid, the hot water, from A to B. So you need a crack or a fracture network. And, well, you slam a 2-kilometer big asteroid into Devon Island, which is what this probably was formed from, and you highly fracture and fault the landscape so fluids can go through. And then you get all the little red dots, and the more interesting ones, you'll see they're all around the outside. They're not in the middle, so they're not random. And these are kind of iron oxide, basically rusty patches that we see all around the rim of the crater. And these are what we think were basically hot springs after the crater formed. And so if you could take that Haughton crater, cut it in half like you would a pie, and then look on it from the side at a cross section, we've come up with this kind of schematic idea of where the hydrothermal deposits are formed and where the fluids would have gone. And so, if you excuse me, and I'll try and speak up. One of the most interesting things we think is around the rim of the crater, where in these big craters the crater collapses inwards along these series of faults, and this is where we think all the hot springs were probably located. Again, it's a different challenge studying impact craters. If you study volcanism, you can go and witness them erupting today. We don't have that luxury, which you could argue, thankfully, we don't have that luxury because it means we haven't had a big impact event. But we're kind of left with the detective story of looking at the rock record. But this becomes interesting for when we want to go and look for hydrothermal deposits on other planets. And of course, the primary place we're looking for is Mars. And so a question here, Mars has those two ingredients. It has impacts, and we know for a fact it has H2O. So at the present day, liquid water, as the Americans, I still hate saying that term. Water to me is liquid, but generally we in the community talk about liquid water. Is not stable on the surface of Mars today, but we know from various space missions, both from orbit and that have landed on the surface, that there's lots of ice. And of course you have the polar caps that are visible even in telescopes. So we know there's lots of water around, mostly frozen today, but even at the present day, if you slammed an asteroid or a comet into the surface, you deposit that heat, you could melt that water and generate one of these systems. And we're looking, and this is one paper that came out in 2010, and I forget who earlier on, we were talking about the high-rise. We're only able to do this now because we have just amazing imagery from the surface of Mars. On the two bottom images are high-rise images, and just look at the scale bar if you can. You don't even need to see it, but this is 25 meters. And so we have a camera around Mars that can resolve, yeah, this is 4 pixels. This this podium here. So we can see things not much bigger than this podium on the surface of Mars, which is really quite incredible. You may have seen pictures from orbit of the various Mars rovers. Recently, this camera was used to find and locate the Schiaparelli probe, the European probe that hit Mars a little bit too quickly. But that probe, they saw the rays coming out from where it hit. But it's an amazing scientific tool to have. And of course, unlike high resolution imagery on Earth that you pay hundreds of dollars for, NASA just releases this all publicly within a few weeks usually of it being obtained. And so I know at least one gentleman in the audience who whittles away many hours looking at these high-rise images. But it's an amazing data set that actually you can just go online and look up these images. And so the kind of mound on the right we think is one of these fossil, and I'm using the term fossil because it's not active now. But so we also have other sense, so this is an image. There are other instruments in orbit around Mars that can tell us about the mineralogy and the chemistry of the surface too. And we've found evidence for clays and other minerals that need water around to form. And so you put all of this together, and it seems that we do indeed have evidence for hydrothermal deposits in impact craters on Mars. And so I'm going to wrap up fairly quickly and kind of come back to this and back to the origin of life. And so, again, you don't really need to read it, but on the left-hand side is just the first billion years of Earth history, broken up into kind of 100 million year increments. And there's a time that is on the screen at about 3.8 to 3.9 billion years that we call the late heavy bombardment period. It's quite contentious at the moment, actually, as to whether this actually occurred or not. But regardless of that, we know that probably 10 to 15 times more asteroids and comets struck the Earth during this part of its history than they do today. And so again, I'll pose that question again, kind of how and why did life originate? And so in terms of the origin of life, kind of if you follow this story, the general, of course, this is science and there's good scientific debate, and some people propose life originated in fairly cold environments, but I still think the bulk of the community thinks that life arose in these hydrothermal environments. And still the one, if you kind of Google origin of life and hydrothermal online, you'll probably come up with pictures of the black smokers that we see at the bottom of the ocean floor. I always like pointing out, and I don't know if any of you have read Origin of the Species. I took it with me on one polar field trip because I knew I had a couple of months in a tent. It's quite a thick read of Victorian English, but he was, I mean, a century ahead of his time. And he talks about this warm little pond idea for the origin of life. And I think most people think that he wasn't actually too far off. And why is that? Well, today kind of science has helped prove, or at least support that hypothesis. And again, don't expect you to I can't read any of the words on here. This is our tree of life. So all of us in this room are on one tiny little branch of this tree. There are three main domains of life: the archaea, the bacteria, and the eukarya. But where they all meet, you'll see that it's colored red. And both red and yellow, actually. And these are because these are thermophiles. These are heat. So phile is loving, and you'll see phile in a lot of biology and geology and thermoheat. So these are organisms that only can grow and survive at temperatures above 60 or even 90 degrees Celsius. So it gets back to what I said earlier about this hot kind of spring environment. And when you look at this, it's like, well, all of the most primitive, oldest forms of life on Earth are from these hydrothermal environments, and hence why we think kind of the first life on Earth also originated in those environments. And so kind of a couple of decades ago, when people were thinking about this, all we really had to go on was things like Yellowstone and the black smokers and volcanically driven hydrothermal systems. But what I hope my research and that of many others now has shown is that impact events after they form can also create these hydrothermal systems. And what I find most fascinating about that is an asteroid like Ceres. And amazing images we're still getting back from there. You could have any body out there that has some water. They never have been big enough to have active volcanism, and definitely doesn't have volcanism today, but it definitely has been hit by impact. Well, has had impact events and been hit by asteroids and comets. And so to me, it really opens up another large kind of realm of objects out there in the solar system where potentially life could have originated and evolved. I'll just touch on this very quickly. Again, a lot of the evidence that we see for water on Mars is in these clays, these clay minerals that form only in the presence of water. And you'll see on this map that they're all distributed around these big, giant impact craters, thousands of kilometers across on Mars. And so we think these are great places to go on Mars for looking for signs of life. And so when my students and I are at conferences and things and these planning workshops where they have to choose the next landing site for the next NASA or European rover, we're very much suggesting that these are impact craters are some good places to go for this reason. And so there's a summary on the screen if you'd like to read it, but I'll be happy to kind of stop now and take any questions you might have. Where should we? This table. Yeah, go for it.
Charles?
Yep.
Okay, I'll go from creation of life to an event that happened here 12,000 years ago.
Oh.
Younger Dryas.
Yep.
Now, there's all kinds of evidence that there might have been an impact, but
Yep.
there's no sign of any impact.
Yep.
Do you have any comment on this?
So if you haven't heard this idea, yeah, there's this younger Dryas period at the end of kind of when the ice sheets were receding from around here and across Canada, and it is incredibly controversial there's been several papers published suggesting that there's, much like how the Chicxulub crater was formed, they haven't found a crater yet, but there's evidence kind of in archaeological digs and various things of potential evidence for something hitting the Earth. The problem is it's not your typical evidence that we use, and so I am at least on the fence. Probably many of my, hope this is not getting streamed live. Many of my colleagues, straight to YouTube, okay.
No, later.
Yeah. I know many of my colleagues are they'll kind of start foaming at the mouth about this and say, absolutely not possible, can't have happened. I like to take a bit more of an open-minded approach. I mean, the idea they're proposing is that something hit when we still had several hundred meters of ice, and so you kind of almost had a crater forming in the ice sheet, so that the environmental effects were still quite devastating, but you kind of destroy the evidence. And so, it's an interesting one. It needs more work, I think, but it's a very controversial topic in the community right now.
It is.
Yeah. Yeah.
You look at the evidence on Earth and you project that out to what you see on other planets on Mars. How much have you adjusted the information you're looking at on Earth and the way you project it onto other planets with all this new information coming from Mars, from the high-rise camera? And I want to jump to Pluto with that too. Are you looking at, what's the fidelity? Is the fidelity of the analogs on Earth improving in terms of?
Yeah, so good question. When it comes to craters, I think it's an easy. I actually don't use the term analog. I mean, a crater is a same as a crater on Mars, as the same as one on the Moon. You adjust for gravity, so that just means for the same size energy, the crater might be a little bigger or a little smaller, but really the effects of an impact event forming are pretty much the same as far as we know. There are other things, so in other parts of my work, I have students kind of looking at things like gullied gullies and potential glaciers on the surface of Mars, that's where the analogs become more complicated, and you have to think about the different planet that you're on. So you've got to adjust, for gravity, the fact that thinner atmosphere on Mars, so water's can't have precipitation, that kind of thing. Then you go out to places like Titan, where we think there are lakes and rivers, but there are methane and ethane, there are hydrocarbons. I mean, now Pluto's just, I haven't kept up with it enough. I mean, it's just what we call nitrogen oceans and things. I mean, it's just kind of bizarre objects that we have to, you just got to completely switch your mindset and think about different kind of physical parameters. But when it comes to impacts, you're, depending on where you are in the solar system, the velocity of impact will be different and your gravity is different, but really these similar types of processes could definitely happen. Yeah. As far as we know. Yes.
You've emphasized the constructive nature of impacts, and of course it's not just constructive with respect to specific events, but also in a more philosophical perspective. The late heavy bombardment. So much of what we think we understand about how our solar system has evolved comes back to, or is partially anchored by, our acceptance of and understanding of late heavy bombardment. You mentioned specifically, it was an aside, I realize, that there's some controversy about exactly what the late heavy bombardment might represent, or if it even occurred. Would you care to elaborate?
Yeah, so this dates back to the Apollo landings on the moon. They brought back a few hundred kilos of samples, and when they started, so it'd be probably a decade or so after the first Apollo landings, they started dating the rocks that were brought back. And they were just not finding anything past about 3.8 billion years. And so people kept doing that. There's thousands and thousands of age date. And if you believe kind of the context for the samples that the Apollo astronauts brought back, they've used what the Apollo astronauts brought back to date kind of those near-side big basins. So a lot of the big dark patches that you all like to look up with a telescope that are now filled with lava. These kind of giant basins like Imbrium, which is one of the bigger ones, the South Pole Aitken Basin that you can't see. Oriental would be the most famous kind of young example of that at about 1,000 kilometers across. They all, if you believe the age dates, come out at about 3.8, 3.9, at the most 4 billion years. And so it was this proposal, which I think is a great one, that, well, why is that? Why aren't there should be things on the moon 4.5 billion years from basically the birth of the solar system. So, kind of long story short, people also raised the good point though, well, where do we land on the moon? Near side, in all fairly similar terrain actually. And so some would propose that actually one of those giant impact basins really would have turned over most of the near side of the moon, and we could be dating, or things could have been reset from the heat of an impact and doing that. So this is a rationale for to me, one of the biggest rationales for why we need to go back to the moon and get more samples is to date different parts of the moon, and in particular the South Pole Aitken Basin. And there's this Moonrise mission opportunity out there that seeks to do that. So since then, there's been some more theoretical models, kind of solar system dynamics and solar system formation, where they, so if you think about impact cratering through time, we know it started here. This is just a simple imaginary plot, okay, X and Y. Lots of impact events happening 4.5 billion years ago. We're here with a low impact rate. So the question is how we got from here to here. You would think it might be a fairly steady state drop off, and that's what we used to think. So the late heavy bombardment had this happening. We think it dropped off in about 500 million years of relative quiet, and then there was a peak. Now though, there's something called a sawtooth model, which kind of does this. So not one single big peak, but it kind of came down in steps. And then some people would propose that there's none of that, and it just was a steady decrease, and it's a sampling bias from the moon. So, but all of this, again, going back to this talk, has implications for us and when life got originated on Earth. So, geological evolution, huge implications, but also the biological evolution too. So, it's neat. And again, you think, yeah, why do we need to go back to the moon? That's one of the big reasons that I would propose we should be going back.
I have a question.
Yes.
Have you found any fossils in your crater explorations?
Yes and yes. Old ones and new ones. I've got
Old ones from before an impact?
exactly, yeah. So, but some of the more interesting ones and new ones that I'll get to. I probably don't have a picture now, but I've got I'm sure you've seen shatter cones that some of these gentlemen have brought in. I've got an awesome one of a nice gastropod, kind of very prominent fossil in a shatter cone. So
That'd be cool.
fossils actually survive impact events. Okay. I'll try and pick one up next time I'm up in the Arctic, Chuck. So it's quite amazing. So the impact of it, I mean, when you melt a rock, it destroys it. But beyond that, the formation of shatter cones doesn't actually destroy the fabric of the rock. But I think more interesting, and is actually something, again, if I was giving a longer talk, there's one of these other bullets up here, is we found fossils that formed actually in glass after the impact. So the impact melted the rock, it cooled very quickly to form glass. Think of, it looks very much like obsidian that you may have seen from that black. It is glass, so it looks glassy. And we found these burrows in there. Think about worm burrows, but on a kind of micrometer scale. And so they're not technically fossils, but trace fossils is what we call them in geology. And we think organisms use the glass for their energy source and kind of colonize the impact after it formed. And so this was a work a PhD student of mine did just a couple of years ago now he published, and it's pretty neat, and again gets to this idea of impacts creating habitats that weren't there before the impact event.
Now, I have a follow-up question to that is, if a fossil can survive an impact,
Yeah.
would it be possible for us to find fossils that originated on the Earth on the moon?
Theoretically, entirely possible. Yep.
So that could really jeopardize our exploration of the moon in a sense that if we find fossils there, and I've heard people hypothesize that there are fossils on the moon, that those would actually come from the Earth.
Yeah, I mean, I think everyone would agree. There was never life on the moon. There's no water around, but there is this intriguing idea that, I mean, for the geologists in the room know this, but we have virtually no rocks. The problem with all of this is we can't go somewhere on Earth and look at that first 500 million years of our history because it's gone. It's been eroded away, recycled through plate tectonics and things, and so decades ago, I think people proposed, well, some of these giant impact basins, let's say we had a big impact event on Earth 4.3 billion years ago, and if there was life there at that time, some of that evidence for life on Earth may have got ejected as meteorites and be Earth meteorites on the moon. So kind of flipping entirely our general approach at things. We have meteorites on Earth, but I mean, rocks have left the Earth too. And so that's entirely plausible, and people do calculations. I mean, it's some fraction of the regolith in certain places maybe have bits of Earth in there. So, not going to say what happened. Yes.
Our image of geology is essentially a rock on a stone, and whereas a lot of the science now is done through computer simulation. And I was wondering if you could comment on the computer simulation as being used as discovery?
Ooh. I mean, I think there's an absolute place for computer simulations, and in looking at impact events, we absolutely need it. Because again, as geologists, we're looking at the end product. We can try and figure out and hypothesize the process that went on, but computer simulations in this instance do provide that kind of visual record, and you can test, of course, so many parameters and things. I do find, and again, this isn't going live now, but there, no,
Yeah.
people, I think too many people fall into the trap though of just taking the output of a computer model as the truth or as fact.
Yeah.
And it's not just in looking at impact craters, it's in kind of lots of fields of science. So again, I'm a big proponent of going out there into the field, looking at a rock. And I mean, I've even had computer modelers come to me and say, well, like the rock's wrong or something like that. Right? And I'm like, okay, I mean, the rock's not wrong, but if I measure the chemistry of this rock with an instrument, I mean, that's what it is. Your outcome of your model is dependent on 10 parameters that you can tweak and get a different outcome. And so, to me, your model should be driven by this, as opposed to the other way around, which does happen, and I think is happening probably more increasingly too. Yeah.
Was the Arizona meter big enough to create the melt that you're talking about?
Yes, but not a lot of it. It's actually been a bit of an enigma at that crater that you don't get this kind of lining of melt. I've had the kind of lucky opportunity quite a while ago now. They don't let you do it, but walking in the ejector blanket of Meteor Crater, and you can only find bits of melt about this big, the kind of little glassy particles that are just strewn around. So, yeah, the melt volume, actually, it was one of Richard Grieve and Mike Dence's major contributions was how impact melts are generated and how they don't scale linearly. The bigger the impact event, the kind of you get proportionally more melt. Yeah, but yeah, no, if you go to Meteor Crater today, especially as a tourist, there's no way you'll see any evidence for that, or shatter cones for that matter, which is still a bit of an enigma for that site too.
I guess my last question is as a geologist, you're used to looking at things in billions of years. Is there any possibility that the events that you've witnessed in your studies could have happened over thousands of years? Or are you 110% certain that all of these events, everything that you've studied, happens over billions of years?
Do you mean the process of formation, or when these certain
Talking about
craters
the
formed?
Overall, like the age of the Earth and all
Yep.
the processes that happened, all the geology that you witnessed, are you convinced that all of these things have happened over billions of years?
I mean, I think yes and no. I mean, Meteor Crater is a good example where we're fairly convinced the dating on that is about 50,000 years ago.
50,000 years,
Yeah,
but like
so that's pretty
a lot
young.
of craters are about 250 million years old.
Again, but there's a huge range.
Yeah, it can go up to 250 million years.
Yep.
But your study in geology overall, what I'm getting at is because there are so many different camps as to the age of the Earth and the age of the universe. Your study tells you that the universe, that the Earth is 4.5 billion years old. And
Yep.
all that you studied in geology says that.
Yes. And I have a good friend and colleague at Western actually who just had a paper in Nature about 2 months ago actually redefining the age of the Earth by 1 decimal point, but it's an important one. But I mean, we have incredibly sophisticated labs for dating rocks of all ages. I mean, again, even going back to craters, there's a really neat one in Egypt that I'd love to go to that they reckon formed just a few thousand years ago. And White Court, we were having a conversation earlier, which is not too far, a little bit.
1,000-ish.
Yeah, I reckon about 1,000-ish years ago. and that's within the realms of humans being around. So they do form today, but they definitely formed billions of years ago, and yep, Earth is 4.56 something billion years old.
Okay, thank you.
Yep.
Just at a guess, for an event like the Chicxulub impact, how long would that area have been or maintained a temperature elevated above what it was before the impact? Like, are we talking centuries? Are we talking decades? Are we talking longer?
So we think for something in the order of Chicxulub, maybe we're into the million, maybe not millions, but something on the order of 1 or 2 million years, which again is when you, because I often get a question, well, unlike volcanic hydrothermal systems that can be active for as long as the magma keeps coming up, these impact events, it's a single generation of the heat source and then it will cool.
Right.
But at Chicxulub and Sudbury, that are both about 200 kilometers across, there's been excellent modeling done that suggests that. But at not Chicxulub, but at Sudbury, some dating done of the actual impact event and the kind of some of the hydrothermal minerals. And there's about a 1 million year time gap, obviously with error, but we're definitely talking hundreds of thousands and probably into the million or so years.
Thank you.
When we visited Western a couple of years ago, Anne-Marie Pickersgill shared her the Apollo thin slices.
Yeah.
So these are samples that were brought back
Yep.
from the moon and thinly sliced and shared around so people could
Yep.
study them. And now I've forgotten what I was going to ask about that.
Moon rocks.
Talk quietly about yourself
Totally fine. Wait.
I did a little presentation on that for the center. When I look at things like that, and suddenly everything becomes very real. For me, I discovered things, but it was just in just a visual sense in a way. Are there still things to learn from the thin slices from the Apollo material?
Oh yeah, and I mean yes, absolutely. There's still, high impact papers coming out, looking at Apollo samples. You think, well, they've all been looked at, but I've actually been encouraged myself to come on down to Johnson Space Center where they all are and look at these rocks, because half the collection hasn't been looked at in much detail. And as we develop new lab techniques, we're able to analyze much smaller volumes or things in much detail. The best example I always would give is water on the moon. We used to think the moon is dry as a bone, as in kind of zero water. But thanks to modern techniques, it's a few years ago now, but they would analyze actually these famous glass beads that some of the astronauts brought back, and they have a few hundred parts per million, which may not sound a lot, but it is quite a bit of H2O in them too. And 40 years ago, that technique didn't exist to analyze those rocks, so that's one thing. But then it's also kind of the next generation going back and coming up with new questions to ask and things for these samples.
So it's good in the sense that they're preserving samples for future generations.
Exactly.
To work
Yep.
on new techniques.
Yep.
Great.
Yep.
Do you have graduate students wondering if they'd like to revisit old studies, or are they always encouraged to be cutting edge and new studies?
I like to encourage my students to do both. Yeah, maybe not really.
It's a career-oriented thing.
Yeah, not maybe doing the same study in the same way, but looking at the same rocks in either with a different viewpoint or with a different technique and thing, I think is definitely valuable.
Is that used for training, and then they can do the more, hate to say call it advanced work, but work that has not yet been done yet, but use the older samples and new techniques to hone their investigative skills?
No, but there's tons of new work to be done on these older sites too. I like to point out, again, I do to my students, but in other talks, the Canadian impact record is a good example of that. So there was a flurry of activity where most of the craters in Canada were discovered in the late 1960s into the mid 1970s. They were visited, but often only visited once. A couple of, maybe one paper, maybe a handful of papers written on them, and then that's it. So you could, as a student, go to literature and say, well, everything's been done on this site. But, I mean, I've gone back to a number of these sites now, and there's still a gold mine of more information to be worked on. And it's not just with new analytical techniques, it's also because just our understanding of impact processes, in this case, have advanced in the last 40 years. And just because often there is a lot of craters, they're hard to get to in Canada, and there's one single paper on them. So there's tons more work to be done.
Who does that work, though? Is it something you encourage students to do, or is it something that the sage professor has to go out and do themselves? How do you get this reinvestigation done?
I mean, I have to drive it in the end, but I take my students along, and there's those students who are lucky enough to go in the field, and then others who will work on the samples too. So yeah, it's a bit of both. And I mean, I know, again, Chuck's flown over many of these sites in Canada, and can tell you how remote a lot of these, the Canadian impact craters are. But I mean, that's also why I love my job as a geologist and a researcher, and get to go to some amazing parts of Canada. I mean, Northwest Territories, Nunavut, Northern Quebec, Northern Labrador. They're hard to get to, which means there's not a lot of work done, and so, yeah, there's doors wide open for new studies.
I realise we're live, so you may want to consider answering this question or not, but just briefly, would you care to give us an idea of where your current research directions are?
Yeah, no, I mean, that's probably not that, it's probably fairly public anyway if anyone were to look at what I do. I have kind of, if I look at what my students are doing now and kind of where my research direction is, as I mentioned earlier, I do have quite a growing program at Sudbury, working with some mining companies kind of hand in hand, answering some scientific questions and hopefully maybe finding them some new ore deposits. So the economic side of things. I still am working slowly through, hopefully before I retire, I'll have visited every Canadian crater. There's, again, I had the privilege to work at many of them. I think the ones, we were talking earlier about the Clearwater Lake structures, or Lac Eau Claire. If you look at Hudson's Bay, and it's this beautiful two big circular lakes. That's actually a great example of results that we never would have dreamed of. I mean, we now just go and, again, look them up online if you can't, they're of course imprinted in my mind. But two quite big impact craters, big circular lakes, been known for a long time. Again, were visited last before I was born to look at the geology, and they always were assumed to be a double impact, two asteroids coming in at once. It was just 2 years ago they were redated as being 200 million years apart. Totally crazy. Kind of, actually statistically, it's something like 1 in a billion, and you've got much more chance of winning the lottery than that actually happening. But again, the science kind of shows us that they're different ages. So lots of Canadian craters, lots of studies. I do have students working a lot on craters on the moon, craters on Mars, and also other processes on Mars in particular. I do a lot of work looking at glacial landforms and gullies and evidence for life. Meteorites too. I have some students looking at actually more Apollo sample work, getting back into how the moon formed and kind of the giant impact hypothesis for that too. So pretty varied, but it's one of those things is never. And then, I mean, in planetary science in particular, I mean, well, I could put 10 students to work on Pluto now. I mean, you get new missions and new data sets all the time. And so it's, I mean, you could just keep going forever, quite literally. But, yep.
Just a final two mysteries for you. The Australasian tektites.
Yep,
It's still a mystery of how, no crater there.
correct, yep.
And the second one I want you to just think about is, if you look at Manicouagan, on the north side of it, there are two circular arcuate rivers.
Okay,
Just beside
yep.
it. It was almost like a twin Clearwater Lake crater. And
There's that
to my
little picture
knowledge,
here,
nobody
isn't
has actually gone there to see it. Eric and I were thinking of canoeing up there one day.
Like very close to the
Yeah,
lake,
if you
or
look at the
the?
north side of Lake Manicouagan.
Yep.
I got it on my side too. Look at these two lakes right here.
Okay, I've never heard of that idea before. but,
Well, looking at it, you see, it's almost like a double crater there.
Yeah,
So, just something for you to think about.
okay, actually, well, Manicouagan is on my trip for maybe 2018, so, sorry, on my list. So it's definitely a site I haven't worked at, but again, there's still work to be done there. And at least that one I can drive most of the way to.
Yes, right,
Yeah,
Get a motorboat, don't canoe on it.
yeah, I've been recommended that too.
We
Yeah.
learned the hard way.
Yep. Yep. Thank you.
We're not done with you yet. Just a small token of our appreciation.
Thank you
Actually,
very much.
and thank you very much for coming to see us. It's been our pleasure. And so you can get it back in one piece.
Thanks. That's good. Would not want Air Canada to break this.
They probably will anyway, but the Canada Post got it to my neighborhood mailbox intact, so there's a fair chance.
Great.
Anyway, thank you
Thanks
very
very
much
much.
for coming to see us.
Yep.
And marvelous talk that has my head totally spinning, but it's exactly what it's supposed to do.
Nope. You're welcome. It's been a pleasure, and come back another time.
We'll work on it.
Okay, so now we're going to move on to the presentation of the awards. Sure. I'll give you the microphone too, if you like. No? Okay, so the 2016 Paul Commission Award, Observer Award of the Year.
Can't be here for it?
Sorry?
Which
Oh,
Roman can't be here
yeah.
for?
Yeah, Roman normally would be doing this, and I guess Karen would be doing the next one too, but neither of them are here. So the awards are here somewhere? Aha. Drum roll, please.
Should have had this ready. Sorry.
He's actually managed to keep it a secret this year. I have no idea who this is going to. One person I know it's not going to is me. So Paul, you may win our little challenge. Who knows? And the winner this year is Paul. I believe this is a new record as well. This is the third year in a row that Paul has won this award. And other than myself, who won it twice, I can't think of a more deserving person.
Thank you very much. Thanks, Gordon.
Congratulations.
Thank you. And Eric, when they eat your heart out.
I'm going to propose we just start putting multiple stamps on his existing plaques.
We could do that. We could do that. Yeah.
Do like the license plates, you know?
Exactly, a little sticker. Yeah. Now, Roman decided this year that he wanted to do honorable mentions as well. So we have 3 honorable mentions. Mary Brown, Taras, I'm not going to try the last name, and Bob Olson. Congratulations.
Now, do we have a dishonorable mention?
We could.
I think that would be a great thing for next year.
I nominate.
You were reading my mind. Now, We have the 2016 Best Presentation of the Year. This is again from Roman. And the winner is Carmen Rush. Is there an honorable mention on this as well, or no? There is. Honorable mentions, plural. And the winners are Simon Hamner and Kelly Jordan. Congratulations. And next, what's this? Unofficial Best Image of the Year?
Roman's initiative.
Roman got carried away, didn't he? All the way to Inuvik, I think.
It says I'm a
Yeah.
Ah, there you go, Eric. A nice image. And Astronauts, Best Article of the Year, selected by Karen, is Stuart Glenn for Stu's Reviews. Congratulations, Stuart. Thank you very much. I hope you've all enjoyed it. The presentation was wonderful. It's been a great meal. Thank you to our hosts. It was absolutely amazing. We'll come back next year. Thank you.